a common application in life sciences, etc., is exponential growth and decay. So you all are kind of probably a bit familiar with this already, maybe haven't really seen it in a calculus context, but we're not actually going to be doing very much calculus with it. We're just going to sort of show how these things are really related to derivatives. So when you're talking about exponential growth and decay, that comes out of a rule where you've got some quantity y, and the rate of change of y is proportional to the size of y. So for example, population growth, right? How the rate of change of the population is proportional to the number of people or bacteria or whatever your population is. So it's proportional to the population. So the rate of change, you guys know rate of change is a derivative. So here we're thinking about perhaps something that is changing over time. So y is going to have a function of t. So if I've got y as a function of t, and then its derivative, its rate of change is going to be dy dt, and then we're saying that this is proportional, so there's some proportionality constant k, so dy dt equals ky of t. In fact, I'm just going to get rid of this y of t here, just to write it as y this way. So this is a differential equation, because it is giving us a relationship between a function and its derivative, and we can, once we know more, we'll actually be able to solve differential equations. Probably you won't really see much of that unless you take differential equations class, right? Which is you can take a little bit later once you've had a couple other calculus classes. So we're not going to solve this. By Calc 2, you'd be able to solve this. This is very easy to solve. But we're not actually going to solve this. We're just going to kind of think about it, and we're going to solve sort of by guessing and checking. And if you think about this, what function do we know where taking the derivative pulls down a constant in front of it? Well, right, the exponential function, right? So if I have e to the kt, well, I probably should make my k like that all the time. So if this is the thing, if this is my possibility, then dy dt, ddt of e to the kt, we know this is k e to the kt, right? So if this is y, then this is going to be ky. Right? So that's basically like a great guess for the solution. You can be more general though, remember, because often we have constants, right? In this case, if I put plus c here, it wouldn't work, right? Because the derivative wouldn't have a kc on it. But if I want to be most general, it turns out the best way to have this thing is y equals ce to the kt, where I'm multiplying by a constant. So if I've got this, then you can see that dy dt, the constant just goes along for the ride for the whole thing. Dy dt is then ck e to the kt. So this is just k times ce to the kt, which is ky, which is exactly what we want. So this satisfies this differential equation. In fact, all possible solutions of this differential equation are of this form. Okay? And we can say one more thing about this. We can say exactly kind of what this C is, because look what happens if I take this form and I let t equal 0. So let t equal 0. What I have, y of 0 is c e to the k 0. So that's just c, right? Because k times k to the 0, e to the 0, sorry, is 1, right? So, in fact, rather than writing c, we often write y of 0 or y sub 0. So, let me just get this straight for here. I'm going to write it up here. We have the equation dy dt equals ky, and our solution is going to be y of t equals y naught e to the kt. Okay, so I think sometimes your book writes it as y of 0, and sometimes it just writes it as a constant y naught. So I tend to write it as y sub naught. So that's just the general idea. Now, what kinds of problems can we do with this, right? I mentioned one of them already. One is population growth. It's not the best model of population growth because it doesn't really include deaths. So there's various better models of population growth, but this is a good model of population growth for sort of a most simple population, like bacteria in a petri dish or something, where it just sort of works out that is a good model for that particular simple situation, right? So it's basically like the first kind of population growth model is this exponential growth. Another thing that you can think about in terms of exponential growth is something you've probably seen already, is continuously compounded interest. So sometimes you'll see problems with that, where this is what you want to do, is use a solution of that form. Both of these situations, this constant k, or a k, by the way, this is called a growth rate in this case because k is positive. So if k is positive, of course, you have exponential growth, right? So this is called the growth rate in this case. Now, on the other hand, k could be negative. So if k is negative, then you have a decline, right? And problems like that you might see, for example, radioactive decay. So in radioactive decay, you're looking at a population also, but you're looking at the population of the radioactive material. And over time, of course, it decays and becomes less radioactive. So this is a situation where k is less than 0, and then k is typically called like a decay constant or something like that, rate of decay. Another situation where you might see that is like cooling of a liquid. Or just cooling of anything general, but often liquids are ones that we use. Newton's law of cooling actually ends up giving you an equation which can be solved in this form, but you can just think about it. I'm leaving my coffee cup out, and let's see what the temperature is of the coffee cup over a set of time. So what I'm going to do is I'm going to write 1 or 2 problems on the board, and I'm going to do a little video for each problem. Okay. Probably I'm going to do one with population growth and one with radioactive decay.